Hi. Okay, so we've been talking about relations, and relations can seem a little bit abstract. So I want to sort of go back and have a relook. So relations are best thought of as a generalization of functions. They're functions where you don't have this restriction on the first element. It's not required that for each input there be exactly one output. If you have, for example, a database, it may be the case that for each person in the database there are two phone numbers or three phone numbers or four phone numbers, or it may be the case that there are some people in the database where there's no phone numbers at all. So a relation is a generalization of a function. And we looked at the particular case of binary relations where there's an x0 comma x1. That's a special case that will matter a lot to us. And in particular, when we looked at binary relations, one of the ways that we looked at them is we considered a class of binary relations, a sum of the binary relations that satisfy three conditions. If a binary relation satisfies three conditions, then we call it an equivalence. The idea here is that we want to consider a mathematical problem in some sense solved, whatever that means, when we are able to break the universe up into cases. And I named a couple of examples, but surely the one that rings the most sort of true is when you say that a linear system can have one solution, or it can have infinitely many solutions, or it can have no solutions. So we've broken the universe of linear systems, all the linear systems that are possible, up into three categories: those with one solution, those with infinitely many solutions, and those with no solutions. So we've in some sense split the universe up into these three discrete cases. And a linear system can't be, both one solution and infinitely many. That doesn't work that way. And furthermore, every linear system falls into one of those categories. So what we want to see now is we want to see a connection between equivalence relations and what we're about to introduce. And there is a very strong connection between equivalence relations and what we're about to introduce. What we're about to introduce is called partitions. The idea with a partition is that it explicitly tells you how to break the universe up into parts. Okay, so something is an equivalence relation if it satisfies these three conditions: reflexive, symmetric, and transitive. Reflexive, symmetric, and transitive, three separate conditions. And of course, anytime you introduce something new, you need to practice it a little bit. So we practice a little bit with those three conditions. A binary relation that satisfies those three conditions is an equivalence. And again, how does that tie to breaking the universe up into cases? Well, exactly what we want to talk about today is how that ties in. Okay. So partitions. A partition of a set U, think of U, for example, as being the collection of all linear systems, or U could be the collection of all numbers, let's say real numbers, or U could be the collection of all triangles in the plane. So U is some collection. A partition of the set U is a collection of subsets of U, P0, P1, etc., that are exhaustive. If you union all the P's together, then you get U. So everything in U goes into at least one of the P's, and disjoint, that no two P's overlap. So everything in U goes into exactly one of the P's. You can't be in two P's, that's what this says. And furthermore, you got to be in some P, that's what this says. So the picture is here. The universe, of course, is inside of the rectangle, and I've broken the universe of all possible lowercase u's up into cases. Some lowercase u's go in P0, some lowercase u's go in P1, some lowercase u's go in P2, some in P3, etc. Okay, so we have somehow broken the universe up into a bunch of cases. I'll sometimes call each of these the parts. So this would be the first part, or the third part, whatever. And again, obviously, with any abstract idea, you need to make it concrete. You need to see specific examples. So here we go. I took the set of all integers and I partitioned it into three subsets: P0, P1, and P2, where P0 is the set of numbers that leave a remainder of 0 when divided by 3. There they are. Every number in there. I didn't list them all because you can't list them all, but I listed 4 of them. I listed some numbers that fall into the collection of things that leave a remainder of 0 when divided by 3. And down here is the collection of things that leave a remainder of 1 when divided by 3. And down here is the collection of things that leave a remainder of 2 when divided by 3. So I've split the universe of all numbers up into the three possible things that can happen: case 0, case 1, case 2. And so in some very small way, in some sense, I completely understand everything that can happen with the integers with respect to remainder of when divided by 3-ness. It wasn't very hard to do, but nonetheless, in some sense, I've broken the universe up into everything that can happen. So more examples, not too many more, but enough to give a person some sense. So if, for example, I take the real numbers as the universe, then P0 could be the set of positive reals, P1 could be the set of negative reals, and P2 could be just 0. So there's only one thing in P2, just the number 0. Then the PI form a partition of the reals. It is the case that every real number goes in at least one of the three. That is to say that the PI are exhaustive. And it's also the case that no real number goes into more than one of the P's. So the PIs are disjoint. All right, next example, let's look at the set of natural numbers where so n sub I is the set of natural numbers where the absolute value of n minus I is less than 5. So for example, n3 is all the natural numbers that are within 5 of 3. See the subscript 3 on the end? So all the natural numbers that are within 5, less than 5, of 3. n15 would be all the natural numbers that are within 5, less than 5, of 15. So 11, 12, 13, 14, 15, 16, 17, 18, 19 for n15. Now, these NIs don't partition P. Sometimes in order to understand what something is, it's just as useful to find a case that violates the rule. Exactly why the NI don't partition N is because they're not disjoint. It's very easy to find a number that's within 5 of 3 and within 5 of 4. That's, in other words, in both of the two capital N subs. Okay. Back to another example of something that is a partition. So I'll let you be the universal set be the set of plane triangles, regular high school geometry triangles. So I have one here and I have one here, and I have all kinds of plane triangles all over the place. Let each part PI contain all the triangles that are congruent to each other. You remember congruence from high school geometry. Pardon me. P0, for example, might be the set of all 3, 4, 5 triangles. So a familiar case, the 3, 4, 5 triangles, and there's a 3, 4, 5 triangle here, and another one here, and another one here, and this one's kind of turned upside down, but it's still a 3, 4, 5 triangle. They're all mutually congruent. So they all get thrown into the same part, namely P0. So each part, PI, contains all the triangles that are mutually congruent. The collection of all such parts is a partition of U, because every triangle goes in some part, because every triangle is congruent to itself anyhow. And no triangle goes in more than one part, because if you had triangles that are congruent to each other and other triangles are congruent, you'd smush them together, it'd be the same part by definition of PI. It contains all the triangles that are congruent to each other. Okay, so what I've done then is divide the universe of all plane triangles in high school geometry up into different parts. There's a 3, 4, 5 triangle. There's a 7, 12, 13 triangle. All kinds of different triangles. There's this oblique triangle, all kinds of different triangles. Okay, and then the important theorem that connects what we talked about in the last video to what we're talking about in this video. Every equivalence relation is associated with a partition, and every partition is associated with an equivalence. So every equivalence relation induces a partition. That is to say, for every equivalence relation, the equivalence classes form a partition. And furthermore, every partition is in turn induced by some equivalence. For every partition, if you define two elements to be related, if they're together in a part, then that's an equivalence relation. So exactly associated with partitions are equivalences, and associated with equivalences are partitions. So when I said I wanted to think about dividing the universe up into cases, and then I immediately introduced equivalence relations, that's because equivalence relations and partitions are inextricable. Okay, so there's going to be two paragraphs here because there's two things to show. The first thing to show is that every equivalence relation induces a partition. That is to say, for every equivalence relation, the equivalence classes form a partition. And then there'll be a second paragraph, there it is, but we'll get back to it in a minute. There'll be a second paragraph showing the second half. Okay, so we got to show that every equivalence relation, for every equivalence relation, the equivalence classes form a partition. So obviously I'm going to check. Do the set of equivalence classes form an exhaustive list, or are the equivalence classes disjoint? So here we go. So assume that we have some equivalence relation on the set U, and the collection of classes is exhausted, it says, and then of course it thinks about it for a second, and then it says the collection is disjoint, and it thinks about it for a second. Okay. Okay, so the collection of classes is exhaustive because every U in capital U is the element of some class, namely its own class. U is in its own equivalence class. So it's in some equivalence class, so that makes the collection of classes exhaustive. Everybody's in something, namely the one containing itself. To check that the collection is disjoint, what you want to do is you want to assume that you have something that's in 2, and then go on to show that the 2 are equal. So we assume that we have Z that's in the equivalence class of U0, and also that Z is in the equivalence class of U1. And we're going to go on to show that U0 and U1, the equivalence class containing U0 and the equivalence class containing U1 are the same equivalence class. Okay, let's go through the details of that. So we assume Z is an element of the equivalence class of U0, and also that Z is an element of the equivalence class of U1. And then earlier we noted that that Z is an element of the equivalence class of U0 implies that the equivalence class of Z equals the equivalence class of U0. And furthermore, we noted that if Z is in the equivalence class of U1, that implies that it's the exact same thing, that Z, the equivalence class of Z is equal to the equivalence class of U1. Well, then they're all three of them equal to each other. U0 is equal to, U0's equivalence class is equal to U1's equivalence class. So in order to show that that the equivalence classes form a partition, I have to show that the equivalence classes form an exhaustive list and that the equivalence classes are disjoint. I've shown those two things, so the equivalence classes make up a partition. Okay, ready for the second half. The second half is to show that if you have a partition, then there's an associated equivalence. All right, so I'm start with a partition. Then if you define two elements to be related, if they sit together in the same part, then we're going to show that's an equivalence relation. Okay, here we go. So we assume that we have a partition of U, and I want to draw a picture here. So there we go, blank that off. Assume that we have an partition of U, and so we imagine that we have somehow U divided up into parts. Okay, so the whole thing is U, and these are the parts. This is P0, this is P1, etc. Okay, and exactly what we're defining is if we have two things that are together in the same part, U0 and U1, we're saying here that U0 twiddles U1. If two things are together in the same part, then we're defining them to be related. We're going to show that's an equivalence relation, but at the moment we're just saying that when are two things related? Well, they're related when they're in the same part. Okay. Okay, so here we go back again. Assume that we have a partition of U, just like in the picture that I drew, and consider this relation that X is related to Y if there's some part that contains both X and Y. Now I got to go through the three properties: reflexivity, symmetry, and transitivity. See them there? Reflexivity, symmetry, and transitivity. Okay, for reflexivity, I'm going to take an element little u, and I want to show that little u is related to little u. Well, of course, little u is in the same part as itself. Of course it is. I mean, think of the picture. Of course little u is in the same part of itself. Of course it is. Okay, so reflexivity proved to be straightforward. For symmetry, in order to show symmetry, I always have to do the same thing. I assume that U0 is related to U1, and I go on to show that therefore U1 is related to U0. All right, so U0 is related to U1, then the two of them are together in some part, just like in the picture that I drew. Well, they're together in some part, so U1 is together with U0 in that part. So U0 is related to U1. Excuse me, U1 is related to U0 also. Okay. Okay, so those two are, they almost fall under the category of so easy that you're left scratching your head and saying, what exactly did we prove there? Kind of stuff. Transitivity is a little less transparent. So let me go back to the videotape, back to the drawing. So for transitivity, I have here that the first one is related to the second one, and the second one is related to the third one. So of course, you can see what I'm going to say. First one related to second one related to third one. That means that all three of them are together in the same part, and so of course first and third are related. Okay, so we've got to write that down, but nonetheless the idea is clear. So for transitivity, you suppose, as you always do for transitivity, you suppose that u0 twiddles u1 and that u1 twiddles u2. And then we have to go on to argue that therefore u0 twiddles u2. Okay, the picture made it clear, but anyway, just to write it out in words, u0 and u1 are together in some p, u1 and u2 are together in some p hat. I haven't decided they're together in the same p just yet. Here we go. But since the parts are, oh, I said p hat, but it's p prime, I'm sorry. But since the parts are disjoint, different parts cannot both contain u1. So p contains u1, p prime contains u1, so p and p prime have to be the same. So p equals p prime. And so u0 and u2 are together there in the same part, and so we have transitivity, we have all three of them, so twiddles and equivalence. Okay, so the sort of global lesson here is that when you want to break the universe up into cases, you want to say, for example, as we did with linear systems, that there are three things that can happen. You can do that by either writing down a partition, or you can do that by defining an equivalence. It will often be the case that defining an equivalence is convenient. When you define an equivalence, the equivalence classes then give you the partition. Okay. Okay, one more thing to talk about. So we've seen that equivalence classes often have multiple descriptions. So for example, for the relation leaves the same remainder on division by 3, those all name that class. So the class consisting of 0, 3, 6, etc. is the equivalence class of 0, but it's also the equivalence class of 3, and it's also the equivalence class of 6. Of course, we saw that, oh, here we go, went too far. It's the equivalence class of 0, and it's also the equivalence class of 3, and it's also the equivalence class of 6, and it's also the equivalence class of minus 3, and it's also the equivalence class of negative 300, and etc. So we could name this part here, we could name any of those names. We could denote it as 0's equivalence class, or as 3's equivalence class, or as 6's equivalence class. That's all. The only difficulty is, that's perfectly correct. The only difficulty is that sometimes when you give something more than one name, it can cause confusion. All right, so we often choose one member from each equivalence class that's natural in some way, and we take that one to somehow serve as the name for that class. Some analogy that I like to make is when you have the states of the U.S., you can think of the capital city of each state as somehow standing for that state, so that Montpelier somehow stands for Vermont. So when we go back to the picture we were just at 30 seconds ago, when I look at all of the numbers that are evenly divisible by 3, I might pick out 0 as somehow natural. And all the numbers that leave a remainder of 1, I might pick out 1 as somehow natural in that class, and always call it the class of 1. It's also the class of 4. It's not wrong to call it the class of 4, but calling it the class of 1 sometimes leads to less confusion. And likewise over here, you might call this the class of 2. Now, a person could say something like, well, you choose 0, 1, and 2, but I choose, 6, 7, and 8. Come on, we're just trying to get some work done. So in some sense, 0, 1, and 2 are natural, and so we often fall back on natural. So we'll call that the canonical element, or the canonical representative, or the natural representative are words that you might hear in all those cases. And it's just the most familiar example that everybody in the room has run across for years in grade school. You'll learn to write fractions in lowest terms. That is to say, although 6/4 and 3/2 are the same fraction, we often prefer 3/2. So we spend a lot of time in grade school practicing how do you write fractions in lowest form. Exactly what you're trying to do is, from among all the different names for the same fraction, you're trying to choose the canonical representative so that, frankly, your teacher finds it easier to grade the homework. They don't have to say, wait, is that the same as 3/2? You just write 3/2. Just the picture, I'm not going to skip back to it because I've already skipped to it 3 times. For the partition of the natural numbers induced by equivalence modulo 3, what's the remainder on division by 3, we might prefer to name the class as 0, 1, and 2. I could name it 6, 1, and 2, but there's something more natural about 0, 1, and 2, and it's just a convention, but it's a very useful convention. And then finally, if we partition the integers into the positive numbers and negative numbers and 0, we might choose the 3 canonical elements to be 1, -1, and 0. And again, you could choose 100 if you insisted. You could choose 100 and minus 62 and 0 as the canonical elements if you really wanted to. But come on, this is sort of the natural thing to do. And so we'll often do that. We'll call that the canonical element of each class, the canonical representative of the partition. Okay, very good. So that takes us through the equivalence classes and partitions. And the most important fact about equivalence classes and partitions is the way that they're tied together. When you want to divide the universe up into different possibilities, that's to say when you want to completely solve some abstract, some mathematical problem, what you want to do then is you want to look for an equivalence relation. You want to say these things are equivalent if. So these linear systems are equivalent if they have the same number of solutions. So this linear system has a unique solution, this linear system has a unique solution. They are equivalent with respect to that particular relation. This linear system has infinitely many, this linear system has infinitely many. They are equivalent with respect to that particular relation. That gives rise to a partition. Okay, very good, very good.